Everybody. It's my pleasure to have our external speaker today, Reid Kelterborn. He is registered professional engineer with a background in designing high-end residential and commercial structures while he was working at Blackwell, and this is a Toronto-based engineering firm. And then he worked, I think, for a few years in China as a technical advisor for Fiat China, and this is a crown agency of BC, where he supported the growth of the wood construction market in China by working with local design professionals to educate and promote the benefits of buildings with wood. He has technical experience. He has experience in technical sales also of engineering work products while working in Metsä Wood. This is the largest forest product company in Finland. And now currently his position is that he is working in the national education. He's the national education manager for the Canadian Wood Council, which is a government organization with mandate to expand wood education in Canada. And I have to say that Reid is a very strong supporter of Western. He came a few times to Western in person, giving lectures to our classes. And also we are very grateful that through him and the Canadian Wood Council, he is currently supporting a course that offered on wood structures. This course will be offered for both undergrad, fourth-year undergrad students, and also for graduate students. So consider these courses if you haven't registered yet. It will be a very good course. And so again, thank you, Reid, for this kind of support. Okay. Now I'm going to pass it to Reid so we can all enjoy his presentation. Okay.
Thank you. So I'll share my screen now. Sorry, I think you have to enable me to be able to share my screen.
So probably Reza can do that.
No, please try again, Reid.
Okay. Okay. Good afternoon, everybody. Thanks for attending this talk. As Dr. Eldamadi mentioned, my name is Reid Kelterborn. I'm the education manager for the Canadian Wood Council. So I figured I'll talk to you today about some applications of wood design and construction, and talk about some trends in construction as a whole, and also some trends in wood construction around the world and in Canada here. So for those that aren't familiar with the CWC, it's a not-for-profit, non-government organization that basically represents the wood products industry in Canada. And our mission is to really increase market access and increase demand for Canadian wood products. We do that through excellence in codes, standards, and regulations. So we help develop building codes and CSA OD6. We also do education outreach. A bit about myself. As mentioned, I started my career as a structural engineer, designing mostly high-end residential projects. These are some of the nicer projects that I designed that you can see here. These are kind of very high-end homes. The one on the bottom and on the right were designed by Bullen Zawinski Jackson, which is a well-known architect from the US, and they designed Bill Gates' house. So it's very exciting working with them. Not all the projects I worked on were this nice, but there's one consistent element, and that was that they were mostly built out of wood, light wood frame with some heavy timber elements, and often had quite complex structural systems to meet architectural needs. I also worked and lived in China for 4 years. And so I was working for the BC government promoting building with wood in China and encouraging the Chinese to buy BC lumber, basically. The picture on the right there, it's a shake table test at Tongji University, just outside Shanghai. And so it's a steel structure they were testing with the infill light wood frame system and a kind of a friction slip fit to dissipate the seismic energy. So it's kind of a neat system they're testing there. Today, China has kind of the leading edges of wood construction with some beautiful mass timber projects, and they also have kind of very basic wood construction in the form of bamboo scaffolding just lashed together with wire. It's simple but effective. While I lived in China, I also worked for a company that was based in Finland that made engineered wood products, so glulam and plywood and LVL. And so I became quite familiar with the construction practices in Finland and Northern Europe. And so I've been quite fortunate to see wood construction in different parts of the world. And so for my talk today, I thought I would start by mentioning kind of current trends in the construction market overall, and then talk about some projects in Europe as a snapshot of what's happening there, and then move on to more Canadian projects. I think it's always good we remind ourselves why it is that we should build with wood, and I think first and foremost is because it's a completely renewable and sustainable building material. Wood literally grows on trees. I think it's remarkable a sapling just needs some sunlight and water and nutrients from the soil to grow, and as it grows, it removes carbon dioxide from our atmosphere to help fight climate change. It gives us oxygen to breathe, and in 80 years, just like any other crop, we can harvest it and use it for building material. Now, historically, we've built with wood because it was readily available and it was lightweight, it's easy to work with, and it was relatively inexpensive. And we started building with sticks, basically dimensional lumber, 2x4s, 2x6s, that type of thing. We used planks for sheathing, and that works reasonably well, but it's a labor-intensive process as it's piece by piece. Then things advanced a little further from just sticks to panel products like plywood and OSB. And this enabled more complex structural systems like shear walls and floor diaphragms. And combined with engineered wood products like I-joists and LVL, enabled increasingly larger and taller and better performing wood structures. And now we've advanced even further to mass timber products. So we've gone from sticks to panels, and now we're on to plates. These are products like cross-laminated timber and glue-laminated timber, dowel-laminated timber, nail-laminated timber, and they can act like large plates, and some can have two-way capacity if needed. And they're highly processed products where the naturally occurring defects in wood, like checks and knots and splits, can be controlled or removed, and the quality of the finished product can really be assured. And these are also really large elements that can be made in a factory to almost exact size. And you can CNC the connections in place, and you can CNC holes for mechanical, electrical, and plumbing routing. And they can be shipped from the factory to a job site and craned into place almost immediately. And all of a sudden, you can erect the entire floor of an office building in 1 week, and you don't have to install formwork or tie rebar or have 150 concrete trucks disturbing the neighborhood. You don't have to wait a while to strip the formwork and then reshore. So mass timber construction really represents a promising new opportunity for the construction sector. And this is hugely important because productivity in construction is notoriously horrendous. So this is a chart of most major U.S. industries, the productivity of most major U.S. industries starting just after the Second World War in 1947. And so you can see productivity, basically the ratio of how much you get out versus how much effort was put in, has exploded in most industries in the past 7 years. So agriculture has improved almost 16 times. So you can think of a farm in the 1940s as looks vastly different than a farm today. You know, leverage scale through land assembly and automation and bioengineering to increase crop yields. The gray line there is automotive manufacturing, which is in productivity has increased almost 9 times. So, you know, they've implemented new concepts of flow and standardized designs, aggressively automated to increase productivity. And so an assembly line in the 40s was quite slow and had a lot of people. An assembly line today is quite fast paced, and there's a lot of robots. Retail likewise has increased almost 9 times. Walmart from the 40s looks very different than a Walmart today. Construction, on the other hand, is the orange line at the bottom. So productivity in construction has increased only 10% in the past 70 years. And most of that was between 1947 and 1970, likely to the introduction of power tools and equipment to the job site. Since 1970, productivity in construction has actually decreased. So it's almost embarrassing. You know, and the picture at the top right there is from 1833. And it doesn't look too different than any kind of single family home in a subdivision being built today. A loose pile of material is dropped and a bunch of people go about building it one piece at a time. So we can see not much has changed in well over 100 years. You know, in case in point, we can look at the Empire State Building, the planning, design, and construction of which took just 20 months. And the structure itself was erected in just 410 days. So the contractor used an assembly line type process and used 3,500 workers each day, and they were able to erect the structure at 4.5 stories per week, which would be pretty unheard of today. You know, there was a human toll. They assume about 5 people lost their lives during the construction, but so we've come a long way with worker safety, but in terms of construction efficiency and productivity, we've really lagged behind. And it's kind of important to remember kind of how slow and stagnant construction is when we look at the overall size of the industry. So this year, the global construction industry will be worth about $10.3 trillion. So if you take the telecom industry and the auto industry, combine them together and multiply that by 4, that's the construction sector. So it's a huge market with a lot of money to be made. And we know not a lot has changed in the past 100 years to make it more efficient. And so that means there's really huge economic opportunity, especially if you can find a way to build smarter and build faster. And so what's interesting is that we're seeing tech companies take notice of this vacuum of advancement, because in the tech industry, things are constantly changing and improving and evolving, and we get a new iPhone every year. And so they can't believe that the construction industry is still doing the same thing they did 100 years ago. And now big tech companies like Google, who have a lot of money and capacity and influence, are getting involved because they see huge economic opportunity in changing the way we build. And what's really interesting is they recognize wood as the backbone of that change, not just because of its environmental benefits, but because wood lends itself really well to more efficient industrialized construction. And so we're seeing companies like Katera, which is based in Silicon Valley, they want to change construction through technology, where they control every product and every process. And instead of the old approach where designers and builders are in different rooms and nobody really knows what each other's doing, they want to spend a lot of time at the beginning to kind of establish a systems approach. And so at the tail end, there's only a few people putting this kit of parts together on site. And so we see kind of on the horizon a paradigm shift in construction from its current state to a more kind of industrialized process, incorporating the concept of design for manufacture and assembly. A design approach that focuses on the ease of manufacture and the efficiency of assembly, which is used in the auto industry. And wood lends itself really well to this type of construction. This is Hotel Jakarta in Amsterdam. It's a 9-story luxury hotel that was built out of 176 factory-built CLT modules. So they were installed at a rate of about 12 per day, and the structure of this 9-story building took just 2 weeks. And so again, that was all CLT modules. And so I think it's really important that future architects and engineers and builders have knowledge in wood because construction is changing and because we need to build a lot of new infrastructure. So the World Bank estimates that we'll need 300 million new housing units in the next 10 years. And to meet this demand, McKinsey & Co., a global consultancy, estimates that 15 to 20% of all construction will need to move to modular or offsite means in the next 10 years. So that's a huge potential opportunity for wood construction, given that it's very desirable in these kinds of applications. And there's an additional problem that young people aren't going into the construction workforce like they have in previous generations. There's a huge shortage of skilled trades in North America, and this further reduces the construction productivity and makes things a lot more costly. The Wall Street Journal recently reported that they estimate about 40% of construction jobs postings remain unfilled even after about a month and a half. So what's happening is older skilled trades are retiring, and the young people aren't going into those lines of work because they don't see it as a rewarding career path. And it's gotten so bad that Hilti, which is a multinational construction fastener and equipment company, they've created an autonomous robot to drill and core concrete slabs because there just aren't the workers that want to do that. And it's very costly. So they've created a robot to enable that to be done autonomously. And so one possible solution to this issue is to bring construction off-site and into a factory. And so basically to create more industrialized processes similar to the automotive industry. And so to kind of illustrate how this can happen, I'll give you a snapshot of what's happening now in Northern Europe in wood construction, where a lot of prefabrication has been used over the past couple decades, and it's being improved kind of constantly. And when we talk about wood construction in Europe, it's good to know the regional differences. So CLT construction is much more common in Southern Europe, Italy, Switzerland, Austria, and because that's where it's produced. And in Northern Europe, they use a lot more LVL, and because that's more commonly produced there. And it's always good to note that there's a lot more LVL produced each year. About 4 times the amount of LVL over glulam or CLT is produced annually. And in Europe, they have 2 different types of LVL. So they have the standard LVL where all the veneers are in one direction, and this can be used for a beam or a joist or a column. They also have a LVLQ, which is where 20% of the veneers are perpendicular. And so that gives it 2-way capacity. So it can be used as a panel or a shear wall or a plate. Now this is a video of an LVL mill in Finland, and it's just good to see how this is a manufactured process. So they start with logs. These are spruce logs that are about 2.5 meters long, and they go into a lathe. So they spin it around at a very high speed, and they basically peel the log into a sheet. And so it's 3 millimeter thick veneers. And then what they do is they dry the veneers down to very low moisture content. So all the shrinkage happens at this point. And then they're also able to grade the veneers. So they take a picture of it, and they look at where the defects are, where the knots are, and they can remove those defects, and they can really ensure the quality of each piece of veneer. And then it goes into a layup process. So here's where they're going to add all the veneers together. So they add a phenolic resin, is an adhesive that's applied to each veneer. And then they just stack them on top of each other to the desired thickness, typically between about 20 millimeters to 75 millimeters in thickness. And so it's just one continuous billet. And they add heat and pressure, and that cures the glue. And then when it comes out, you have this huge billet that's a solid kind of homogeneous piece of wood. And from there, they're able to saw it into different widths and to different lengths. And they package it and send it all over the world. So this is in Finland. Some of this material that could be going as far as Australia. to Australian markets. So it's really a global product. And over the past kind of 15 years, prefabricated elements in Northern Europe have become more and more common. And one particular is a stress skin panel element made from LVL, entirely from LVL components. And it's excellent. It has really high strength to weight ratio, and you can get very long spans, up to 20 meters as possible. It's a lot lighter weight than CLT or concrete for that matter. And because it's made in a factory, there's very little waste and there's very few errors on site. So stress skin panels has three kind of common configurations. They all start with a LVLQ top panel. So this is basically a compression flange. It's then glued, structurally glued to ribs. There's a shear transfer, and then so then the ribs go into tension. So you create this kind of composite section. So rib slabs are typically used for uninsulated roofs. Box slabs are used for insulated roofs. They can add insulation in the factory. And then an open box slab is typically used for floor systems. So, it really comes down to material efficiency, similar to a steel W shape or I-beam. The composite section, it's really putting the most material where it's structurally useful. So we know, they make I-beams for a reason. Just to give you an idea of kind of how efficient the stress skin panels can be, this is a floor system spanning about 8 meters. So you can see that an open box stress skin panel is able to span that 8 meters in just 58 kilograms per square meter. CLT, is 3 times that. So CLT is great for certain applications, but for long floor spans that are going to be vibration controlled, it's not an efficient use of material because it's a solid square section. It's just not efficient use of material. And cast in place concrete, is over 6 times the weight. So this just kind of exemplifies how wood is good for kind of offsite and prefabrication because how lightweight it is. It's easy to get to the job site from the factory. And these panels can be made in a factory with very simple hand tools, handheld power tools. Only about 30 minutes per square meter of factory labor is required. This is a company in Belgium that has made kind of a semi-automated assembly line process to make these stress skin panels. And so they start with a jig and they install the ribs. And then they add so this is a polyurethane adhesive that they use to glue the top panel to the ribs. And so that's a cross-bonded LVL top panel. It's continuous. So that'll go into compression. That's basically your compression flange. And they nail it down, and the nails only provide a clamping force until the glue dries. So that the nails are providing no shear transfer. The glue is doing all the work once it dries. So then they install lifting rings so they can handle the panel. And so you see how long that is, 20 meters, and it's probably 2.5 meters wide. So it's quite a large element. You can get a lot of these on one truck because again, they're very lightweight. So it's easy to move around. It doesn't cost a lot. So then it arrives on site and they can just crane it right into place. So you just have a mobile crane and a couple workers on the roof are able to maneuver the panels into place, and then they just screw them together. So, you can install 50 square meters in a couple minutes. So it's very, very fast, very efficient. They build a lot of warehouses and logistics centers. This one is in just outside Helsinki in Finland. So it's about a 12,000 square meter facility. There's a glulam post and beam structure with a stress skin roof system. So they designed it this way for speed of construction. So the whole structure was completed and weather tight in just 10 weeks. And it had an interesting kind of fixed base portal frame system. So the glulam columns had a fixed base, and that created a portal frame so they didn't have to have any internal bracing or shear walls. shopping centers and kind of your Home Depots are done in the same way, similar way. You can see the glulam post and beam structure, and then these would be the stress skin panels arriving on truck. So moving on to kind of a less glamorous agriculture and industrial buildings, the 3-hinged arch. So it turns out that cows are happier in wood structures and they produce more milk. So there's a real trend to make dairy barns out of wood, and they're able to create these 3-hinged arch out of LVL. And so the benefit being is you can use these trapezoidal sections and have a larger cross section where you have high moment and taper down to where you have 0 moment. And the benefit being you get two pieces out of one rectangular panel. And then for the moment connection or semi-rigid connection, they have this circular bolting pattern. The benefit being that every bolt has the same moment arm, so that every bolt's seeing the same force. So kind of the next step of industrialized construction is to not just make ready-made elements in the factory, but completely finished modules. And so this is a company again in Finland called Cisco, and they build basically apartment buildings out of factory-built modules. And so again, they're using entirely LVL for this for these modules. They use LVL basically because it's stronger than dimensional lumber, and it's also has much higher tolerances. So every piece is going to be the same width, same thickness. It's not going to be warped or twists. So the machinery can accept it, and it doesn't cause problems. So here they're making the wall elements. You can see very thick, very deep wall elements to get a high level of thermal insulation. And so then they add, a stress skin panel floor system. So here it's kind of a more manual process. You can see them applying the glue there and installing the top panel. And so then they build these bathroom pods. So again, all the mechanical, electrical, plumbing is done in the factory. So it's plug and play on site. So you can see just the level of finish. They even do the waterproofing and install the tiles in the bathroom and kitchen. And so this is all done in the factory. So it's about 6 days in a factory to build one module. And then you can see them bringing all the pieces together. So all the prefabricated elements. And they even installed the drywall and all the cabinetry, even the appliances. So then it gets put on a truck. Each module gets put on a truck and delivered to the job site. And they basically have concrete foundations waiting, and the modules are craned into place and bolted together. And again, all the services are plug and play. So basically, it takes 6 days in a factory to build, and then 1 day on site to install. And then it's occupied after 1 month. So it's very fast, very efficient construction process. So moving on, this is kind of a less repeatable typology. This is a very special project called the Metropol Parasol in Spain. It's one of the largest wood structures in the world. It consists of about 3,400 unique wood elements. So it's about 75 meters long, 50 meters wide, about 30 meters tall, and it's all made up out of cross-bonded LVL pieces. And so it's not just a sculpture; it's actually a public space. So there's bars and restaurants on the top, and you can actually go and there's a pathway on the top of the structure. And so it's made up of an orthogonal grid of about 1.5 meters by 1.5 meters. And so you can see here the two directions. So each piece is not alike. No two pieces are alike, I should say. So 3,400 different elements. And again, they used cross-bonded LVL. So they used a CNC robot to cut the very kind of unique elements out of a rectangular sheet, so you could get multiple pieces from one sheet. And just for kind of scale, you could see a worker here operating a crane. So just the relative size of the piece, they're quite large elements. And they created a neat connection system. So because the pieces are kind of intersecting, so they had to create this kind of a moment connection. And so they drilled and epoxied in threaded rod. So that goes in about 2.5 meters and then epoxied in. So it's very strong connection. And they've coated it in a polyurethane adhesive or a coating to protect it from the elements. It's a permanent structure, so it has I think it's got a 75-year service life. So you have to protect it from UV and moisture damage. So this is the construction sequence. The two main supporting columns are reinforced concrete. You can see them craning in some elements here. So you can see that grid work, the curvilinear system there. Just for scale, kind of a city block, it's quite a large structure in the finished project there. So moving on, that's a kind of a snapshot of what's happening in Europe. I'll talk a bit about North America now quickly, because and kind of one specific reemerging trend is mass timber office spaces. So this picture is in Minneapolis, T3 building. So it's about 180,000 square feet. About 100 years ago, we built a lot of what's called brick and beam buildings. So this is a masonry exterior with a heavy timber post and beam interior structural system. And in Toronto alone, there's about 40 examples of these, ranging in height from 5 to 8 stories. And not only have these buildings performed really well over the past 100 years, but they're the most sought after office space. Not just because of the downtown locations, but because people really like working and living in wood environments. And we didn't stop building 8-story wood buildings until 1941, which is when the first National Building Code of Canada came into effect. And it basically arbitrarily limited wood construction to 4 stories or less. And that was mainly because this is what the fire service looked like at the time. So we've come a long way in understanding how how wood behaves in a fire and fire suppression systems and alarms. So there's really no reason why we have to arbitrarily limit wood construction to 4 stories anymore. But anyway, developers have taken note that tenants will pay huge premiums for wood office spaces, and because there's a finite supply, developers are basically recreating them recreating these brick and beam buildings using mass timber elements. This is 80 Atlantic in Liberty Village in Toronto. So it's a 5-story mass timber building that was just completed last year. So you can see it going up. It's a glulam post and beam structure with an NLT deck. It's a 5-story building. Unfortunately, it has to have a non-combustible exit core. And just because that's what's stipulated in the Ontario Building Code. But you can kind of see the finished product. It's quite a nice office space. Similarly, there's a 6-story office just outside Montreal called Synergia Complex. Again, it's a glulam post and beam structure with glulam chevron braces and everything. Well, they've left as much of the wood as exposed to view as possible. It has a GLT or glulam timber deck. So again, it's basically just like a glulam beam, but on its side and working in weak axis. You can see there the lateral system is a chevron bracing, and then the elevator core was actually CLT for this project. This is the bottom story, the braced frame. So you can see here, I thought this is a neat connection. So they're transferring lateral forces from the brace above into the horizontal beam here. So this steel connection is going into bearing against the wood. So they don't rely on bolts because it's too ductile. They want a nice stiff connection there. And so because Montreal has quite high seismic forces, they've used capacity design. So they want ductility. So they've used these really narrow steel pins. So basically in an earthquake, the steel pin will deform and absorb the energy of the earthquake. And you can see they've left a gap here purposely so that the brace doesn't go into bearing, because again, they want those pins to engage and deform. They don't want the wood bearing against the steel, because it wouldn't be ductile. So the finished product there, it's quite nice. You know, it's often kind of difficult to quantify the benefits that people are happier, healthier, and more productive in wood environments. But I mean, an easy litmus test is to kind of just ask yourself, what office space would you prefer to work in? I'll move along here. So kind of one more reemerging trend is tall wood buildings. This is Brock Commons. It's an 18-story student residence at UBC. It was built by a crew of 9 people in just 45 days. So it's a CLT point supported on glulam columns. So the CLT is working in 2 directions. And you can see all the elements arrived on site with the connections already installed, all CNC'd in, ready to go. And it's craned directly from the truck right into place. You know, everything was cut perfectly, so there's no cutting on site. There's no waste or errors on site, so it's very efficient. So just goes together like a big Lego. The project is again reinforced concrete, just because it's 18 stories tall. And again, the benefit of kind of prefabrication offsite construction is that there's no guesswork on site. Everything comes and it's cut to exact size, and it just gets craned into place immediately. You know, and inevitably people say, well, if we build more buildings out of wood, we're gonna run out of trees, and the answer to that is actually no. The wood fiber to build Brock Commons was grown in our forest in just 6 minutes, so we're not going to run out of trees. Canada has a significant amount of forest land that's very well protected with strong regulations. So for every tree that's cut down, about 4 are replanted. And so we actually lose far more of our forests to fire and insect attack than we do for harvesting. So less than half a percent of our forests in Canada are harvested annually, whereas almost 5.5% are lost to forest fire and insect attack. So at 53 meters, Brock Commons is pretty impressive, and kind of a really good example of tall wood construction and prefabrication. But it actually wasn't the tallest building, wood structure in the world. That was the Yungshan Pagoda in Shanxi province in China, which is 67 meters tall. And for about 900 years, it survived quite beautifully, despite fires and severe earthquakes. And it was the world's tallest structure until just last year, when a hotel was completed in Norway at 85 meters tall. And so this is the Mjosundet Tower, which is a hotel and private condo. And unlike Brock Commons, it's an all-wood lateral system. So it has a CLT core and glulam super bracing on the exterior. So there's no concrete core for this project. You can see just how large the columns are. These are 2 foot by 2 foot in dimension columns. So very, very large components. You can see these frames. These are 4-story tall frames being assembled together on site and then craned into place. So it's at the edge of a very large lake in Norway. And again, the corner columns are just huge. These are 2 foot by 5 feet in dimension, and they've left the super bracing kind of exposed in the unit, so you can see it to view. Here's just a quick time lapse. So you can see the frames are going up 4 stories at a time, and then they infill the floors afterwards. And then they follow with the super bracing. So it's very efficient construction sequencing. And the building enclosure goes up not too far behind it to protect the wood from the weather. So I'll just skip along here. This is the last project I'll talk about, and it's one of my favorites. It's in China. It's the Qingdao Pearl Visitor Center, and it just kind of exemplifies that prefabrication and wood structures don't have to be kind of rectangular boxes. They can actually take quite unique shapes. So this is a NLT, or nail laminated timber structure supported on glulam columns. So you can see you have these inclined glulam columns that take gravity and lateral loads because they're inclined and kind of create a frame system. And then the roof is these NLT panels reinforced with this king post cable truss system. And you can see the roof takes this kind of freeform shape, and that's created because the NLT, each this is 2x8s that are just nailed together a fraction of a degree off. And you create this kind of really unique form. So these panels were made in a factory on site and then just craned into place. So you can see the roof from above. So here's the factory where they built the panels. And they just crane these about 10 feet wide, 60 foot long panels into place in the finished product there. So that's going to wrap up my presentation. I guess we have time for a few questions, but if you'd like, you can take my contact info down, and I'm always happy to answer questions if something comes up later. So I'm always happy to discuss further. But yeah, if you have any questions, I'd be happy to answer.
Okay, thank you very much, Reid, for a wonderful presentation. That was really amazing. So we take the questions through the chat. So
okay.
Probably, Reid, we have the first question coming from Mustafa. So do you see it, Reid?
Not yet.
Yeah, he's saying that the moment connections mentioned previously is the Helsinki portal frames, the barn frames, etc., and they are considered commercial connection on each project, has its own moment capacity designed specifically for it.
Sorry, so what's, I missed the question.
I'm trying to understand.
Okay.
Saying, are they considered commercial connection and its own connection? Like I think custom made probably. That Mustafa, do you want to?
Yeah. Hi. Thank you, Dr. Ashraf. Thank you, Mr. Reid, for the presentation. My question was the moment connection mentioned previously in the Helsinki portal frames and the barn frames.
Yes.
They considered the kind of commercial connections, or each project has its own moment connection designed specifically for it?
Yes, so they'd be kind of one-off. They're not kind of proprietary in nature. They'd be designed specifically for those projects. Having said that, there is companies that make kind of somewhat off-the-shelf moment connections. You can look at Rosoblas, which is an Italian manufacturer and fastener company, and they have some different connection systems. Moment connections in wood are notoriously difficult just because of wood being anisotropic and parallel to perpendicular to grain, different capacities. So the moment connections can often be quite difficult. But yeah, you have most often you have success when you're kind of epoxying into end grain, and so you're kind of avoiding a perpendicular to grain compression.
Thank you.
Okay.
No problem.
The second question is about what is the diaphragm behavior of these wood panels?
The diaphragm behavior, so it depends. So for CLT, they basically, the panels, they either connect them through screws. So they'll have screws that are kind of going on an angle and work axially. So that it's kind of a 3D screw. So it's angled in both directions. And so the screws can transfer forces axially and withdrawal. Another way is kind of they recess in a strip of plywood and connect it. So that creates a shear transfer in plane for the diaphragm. So that's for CLT. For NLT, typically they put plywood over top of the dimensional lumber. So if it's 2x8 nailed together, they put a layer of plywood over top, and that creates the diaphragm. Hopefully that answers your question.
Yeah. Next question about fire resistance of the structure.
Sure. So wood's combustible, but the benefit being is we know exactly how it combusts, and it burns at a rate of about 35 to 38 millimeters per hour. And so for these large mass timber structures, they basically oversize the structural elements, so the columns and the beams, depending on the fire resistance rating they need. So depending on the occupancy, so if it's an hour fire resistance rating, or if it's 2 hours. So basically what happens is there's a sacrificial layer of wood that burns and chars. And the wood that chars actually protects the interior wood fibers. So the remaining wood still provides strength and allows the structure to remain standing up, and allows the occupants to safely get out of the building. So that's kind of how fire resistance is achieved through these exposed mass timber buildings. For lightwood frame, they encapsulate it in a gypsum board, and that protects the wood structure. So it's like wood burns, but we can just get over it, because if you can take a lighter to a 2x4, it doesn't exactly catch on fire very easily. What causes fire is the real fuel and real load to fires is all the furnishings and carpet and all that. The wood structure itself actually doesn't cause a lot of the problem.
Okay. There was a next question about cost comparison between a simple 5-story building constructed from wood versus concrete. Design and construction cost.
Yeah, that's a good question. I think there might be a small premium for the mass timber, especially in Canada, just because right now we don't have a lot of manufacturers of mass timber, CLT and glulam. There's more coming online, and so that increase in supply will improve competition. But like you can see, it's a very efficient process. So it's much quicker than concrete, and so it might cost a bit more, but you can get it done a lot quicker, which means you can get it occupied sooner, which means you can the owners can start making money off rent earlier. So right now, I think there might be a small premium, but soon enough, I think it will be at par, or even there'll be a reduction in price compared to concrete.
Okay. I think regarding this question, probably I expect that for light frame, it will be cheaper than concrete, right?
Yes, sir. For light wood frame, multi-family residential, so we're talking 5 or 6 story light wood frame, it will definitely be cheaper than concrete for sure, and probably cheaper than cold form steel stud as well.
Yeah. Okay. Any other questions?
Well,
I have a simple question, Reed, about
Yes, sir.
you mentioned about the efficiency of the construction industry, and that was very interesting graph, and it was really surprising to me to see that the efficiency of the construction industry has decreased.
Yes, sir.
Over the years. Definitely compared to manufacturing has increased significantly. Now, does that mean that the construction was able to provide a lot of job opportunities for people by being not efficient? And if it becomes more efficient, the society is going to lose that?
Well, I mean, Yeah, I think that there's a lot of things that make that go into the kind of decrease in productivity. I think there's just the processes haven't improved, and construction is among the least digitized industries, major industries out there. Certainly compared to kind of the automotive and other major sectors. So the construction industry hasn't kind of harnessed the benefit of kind of embracing technology like other sectors have. So that's kind of one area. But with BIM and kind of automation and this kind of thing, that I think that will really have a big effect on increasing productivity. But then, like I mentioned, one of the major hurdles in the construction industry now is that people aren't going into the skilled trades. So people don't want to go into the construction sector. They don't want to become bricklayers or form workers or iron workers, that kind of thing. It's, I guess, unfortunately, it's viewed as not a rewarding career path, and so that there's really a shortage of skilled labor, and it's only going to get worse as the older generations retire out of the industry. There's no younger skilled trade people going into those jobs. So it's just going to, like I said, there's companies coming up with kind of automation devices to fix that problem. So yeah, I don't think it's going to. And again, I think that the solution is changing the way we build. Not doing it on site as much. You wouldn't build a car in your driveway. It wouldn't make any sense. You build a car in a factory. So there's absolutely no reason why we shouldn't build a building in a factory, because you can control the environment. It's always sunny and 20 degrees inside a factory, and you can control the quality of the final product. You can increase the labor force, because I think a lot more people would be inclined to work in an indoor kind of setting compared to on-site, especially in Canadian winters. So changing the way we build and bringing things off-site and into a factory as much as we can, I think there'll still be lots of jobs, but I think there'll be better jobs. Hopefully that answers your question.
Yeah. Do you think we're going to see one day building done by a 3D printer?
I think maybe one day. Yeah, and they're making lots of progress, and the 3D printing with wood is kind of it's kind of subtractive 3D printing, so they're able to use CNC and robotic fabrication to really accurately make these kind of panels, CLT panels, and all these connections that are very, very accurate. So I don't think it's too far off.
Yeah. Okay. So any other question from the audience? If not, again, thank you very much, Reid, for a very interesting and informative presentation. And as I said, we have now a new course on wood structures, and the materials was provided by the Canadian Wood Council. So I encourage you to consider this course. I think the registration is open now, but there's a cap on the course, so it's going to fill very quickly. Okay, so again, thank you very much all for your attendance, and I don't know if there's a seminar next week or not. I don't think so, Reza. Is there another seminar coming next week?
Yes, there is. Yeah,
there's one more next week. Okay, so thank you very much, and we'll see you all next week. Bye.
Thank you very much.
Thank you, Reid.